Okay, let's continue. So I'm going to repeat the last part. So the focus of this hands-on is to deploy a workload, a really existing workload on Kubernetes using charms. This workload will be OSM itself. So we build charms for each component, and those charms are ready to be deployed on K8s. Okay, so for this hands-on, instead of setting up a big Kubernetes, we're going to use we're going to install microgates. That is a very lightweight snap and very fast. You'll see with your own eyes now. And we will have a single node Kubernetes cluster, which can be used for installing OSM, for instance. Okay, so I'm going to do snap install microgates. Okay. Okay.
So microgates is just a single package Kubernetes. So it has all of the binaries of Kubernetes, standard upstream Kubernetes in a single package. So when you snap install it, you're just essentially getting all of the binaries, the client utilities and the server utilities installed on your system and brought up and running. You can remove microgates with just snap remove microgates, and then it's completely removed from the system. And you can cluster microgates. So if you have 2 or 3 machines, you can actually cluster the microgates entities. And so you can make a small production cluster with microgates. It's designed for essentially edge and IoT and developer scenarios. In an edge scenario, you might have 3 small servers and you make a microgates cluster. In a developer scenario, it might be your workstation and a VM, or it might be a CI/CD VM. So you have some code that you want to test on Kubernetes. Your Jenkins would spin up a VM, snap install microgates, and then run your tests on top of microgates. And IoT, you can imagine this works very nicely in a small robot or appliance, effectively, where developers like to use Kubernetes for application deployment.
So Alex, is like microgates platform is production now?
Did you do status? Did you talk about it?
No.
I see. So if you do microgates.status, then you will see an overview of all of the different capabilities. Do microgates.status now, because you're up and running, right? Right. So here you can see the status, right? You've got microgates itself, and then you have a set of add-ons to microgates, which are useful things for people who work with Kubernetes every day. You've got an add-on for Cilium, Dashboard, DNS, Fluentd. You've got Helm there. You've got Istio there, Jaeger there, Kubeflow there, Linkerd, MetalLB. These are all sort of built into microgates, but they're disabled by default. So you can turn on a capability just by saying microgates.enable and then that capability. And we want you to turn on 2 of them, which are storage and DNS. So microgates.enable space storage space DNS. And so there you'll see effectively the Kubernetes work getting done. And if you then do microgates.status again, you'll now see that DNS is enabled and storage is enabled as well. Okay?
Okay, so just to go through all the steps that I've done, I installed microgates. I did the microgates status, and we could see that microgates.
To do the add user in the new group.
Oh yeah, okay, yeah. First of all, after installing microgates, we have to add the user Ubuntu to the microgates group. Okay, we do that with sudo add user Ubuntu microcates, and then we enter in a shell or with the microcates group.
That's so that you don't have to log out and log in again, right? You've been added to a group, but the shell doesn't know it, so you need to just make the shell aware of that.
Yeah, exactly. So if you do microcates status just after installing it, obviously it's not running yet because it has a couple of services to bring up. So then we can execute microcates inspect, and we can see here all the services that are running, okay, that make our Kubernetes cluster possible. And also, then when you say microcates status wait ready, it will wait until microcates is run, and then it will show the enabled add-ons, which basically all of them will be disabled by default. Okay, and the Juju, when you bootstrap the Juju controller with the Juju bootstrap microcates command, the storage and the DNS are needed, those add-ons. So if you do a bootstrap and you forgot those, then Juju will show you a message and just to enable those, and it's very smooth and very clear process. Okay, so I already have my controller bootstrap on microcates, and I'm going to show that with microcates you can access to the kubectl command just by putting microcates.kubectl, and you can execute commands like, for example, microcates kubectl get all from all namespaces, and that basically okay, and this basically will show you all the namespaces that are created. For example, all the add-ons are added to the kube system namespace.
Can you guys confirm that you can actually read what's on the display, just in terms of resolution and streaming? Okay, great. We'll keep going.
Okay. So yeah, here we can see all the namespaces. All the add-ons are added to the kube system namespace. And now we are going to add a new model to Juju and deploy there the OSM workload. A good thing is that we can separate things in models, so they are deployed on different Kubernetes namespaces, so that we can separate some deployments from one from another, and not having all of them in the kube system namespace, for example.
Sorry, I'm just trying to make that video as well, but I don't know how to do that.
Oh yeah.
It is what it is.
So yeah, so I'm going to, I didn't have the model, but I can check by executing Juju models. Okay, no. So I will add.
So hold on, I think we need to explain that concept. Okay, so a single Juju controller can manage multiple different scenarios. In OSM, we have the idea of a scenario, right? And you can have multiple scenarios managed by OSM. At the VCA layer, Juju calls those different scenarios models. And each model has a collection of applications which can be tightly integrated with each other, right? They can see quite a lot of each other. The assumption is that they're all being operated together for a common goal. Each model is on a specific substrate. So a substrate could be a Kubernetes cluster, or a substrate could be a public cloud, or a substrate could be a Vim, a private cloud. So your Juju controller, it knows about several clouds. If you just do Juju clouds, I think, Juju, right? So this controller knows about microgates, right? Let's do -all. It's only showing microgates because that is where it has models. But this controller also knows about AWS and Azure and Google and Oracle and so on, right? The fact that you can have multiple separate models, right, means that you can keep sets of applications and the permissions associated with them and the data associated with them isolated, and you can give different people or different services access to different models with different permissions. So in this case, Juju is modeling, it has a model on microgates, and it's empty at the moment. We're now going to deploy the charms that make up OSM. We're going to deploy them into that model. Now you can have the idea of like a meta package. So you can have the idea of a set of charms that get deployed together. And so that's what we're going to use. When we say Juju deploy OSM, OSM is a bundle of charms. And so you will see those individual charms getting deployed after Juju has read the bundle description.
So I'm going to deploy now OSM, and it will basically deploy all the charms. Okay, it's now doing it, and then it will add all the relations between all of these components so that every component knows about the related components.
So we showed you earlier a list of events. I just want to scroll up, sorry. We showed you earlier a list of events that are being moved through the Juju system, and here you can see an example of that, right? There is an event when the charm arrives at Juju. There's an event when it gets instantiated for each different charm, effectively. If you look at this, this is telling you that this charm is coming from the global charm store, from the charmed OSM team. It's the LCM Kates charm, and it's revision 37 of the LCM Kates charm, right? And here you can see that there's an event where Kafka Kates got instantiated with a single unit. So it's not a scaled out Kafka, it's just a single unit of Kafka. So each of these is essentially an instantiation event, right? Now we essentially need events to connect and integrate those different pieces, right? If we watch the status, okay, so now what are we doing? We're watching the model status of this model. And it's a distributed system, so things are happening all over the place, right? Each charm in its operator pod is working, exchanging information over those relations, updating relation data, and noticing updates to relation data. So these charms are talking to each other, and they're updating their own status in real time. So here you can see these guys are waiting, right? Kafka is waiting, probably for something else to become active, right? The RO is waiting. Prometheus is active, so Prometheus is up and running and is quite happy, right? These changes to the status are effectively as events move through the system. Each charm is noticing events, and it's doing work, and it's generating events. It might be updating its application data, which generates events for everything that's related to it, or it might be changing its status. Okay, so this is what's going on at the Juju level.
There's a question on the chat.
What's the question on the chat?
If the changes are performed in parallel for all the charts.
Okay, so this is a really important question. Distributed systems are famously difficult. And so we can't avoid the fact that we are a distributed system, right? You may have 100 machines working together in a Hadoop cluster or 500 machines in an OpenStack cluster. So you want to use that parallelism. You want to have things happening at the same time. You don't want to go over to this machine and configure something and then go over to another machine and configure something there sort of in series. You want parallelism, but you also have to be careful. If you have two scripts running on the same machine at the same time, trying to do something that interlocks, for example, update packages or install packages, you can get race conditions and locks. So Juju is a distributed system. It does allow things to happen in different operators or in different charms on different units at the same time. But on any given machine, it only allows things to happen in series. So for example, I may actually have two pieces of software installed on the same machine. For example, I may have an intrusion detection system and a database on the same system. So I would have two charms on that same system. Each of them is responsible for that unit of that application, that unit of the intrusion detection system, that unit of the database. And now I may have a bunch of events coming at both of those units. What Juju will do is on that machine, it will only allow one event to be processed on one of those units at a time. So it will essentially carefully avoid situations where two different charms could be processing events at the same time on the same machine and they both get into a deadlock situation. So Juju's very careful about getting you the maximum throughput from your distributed system, while at the same time trying to avoid the sorts of situations that cause problems for people. As a developer of the intrusion detection charm, it would be impossible to predict that there might be another charm on the system. We want the intrusion detection charm to be usable in as many different scenarios as possible. So maybe there's going to be another charm there, maybe there isn't going to be another charm there. So Juju will protect the intrusion detection charm by being sure that the intrusion detection charm, when it is processing an event, is working on its own. There's no other charm processing an event in the same machine at the same time. Of course, on other machines elsewhere in the system, other charms can be processing their events without deadlocking this charm. Does that make sense? All of the data, the persistence data from those charms does go back to the central Juju controller. And there we do use transactions in a central database to ensure that effectively we maintain data integrity at the controller level. So we have essentially transactions at the controller level, and we have parallelism in the different machines that make up the different workloads or charms, effectively, the operators, whether those are VMs or containers, right? And we have serialization within the scope of a single operating environment. Does that answer your question? Okay, so if we go back to the Juju status now, you can see that that model has mostly settled. Don't tell me, tell them.
Oh, okay, yeah, sorry. The LCM in this case is waiting for something, right? As we can say here.
There's the message.
And the thing that is waiting for is the VCA, because we haven't configured the VCA. So it doesn't matter. For the sake of this presentation, we will show actions and so on. So we won't actually exercise this OSM, but can show something that is really interesting, and it's very related with the answer I gave to a question before. So Kubernetes has a very cool thing that basically it assigns a cluster IP to each application. So in this case, let's say, for example, let's take here the NVI. So here in the app level, we can see the NVI, and it has this IP, this IP as the cluster IP, okay? And also, if we go here to the unit, we currently only have one unit of the NVI, right? and that unit has the IP 10.1.1.440. Okay, so but if we scaled up the NVI, then we will see several units deployed with different IP addresses, but Kubernetes is intelligent enough to load balance the load between all the different NVI units. Okay, so I'm going to show the presentation, the slide I made. Okay. Which is basically this one, in which we can see different containers, workload containers, units, with different IP addresses. And here we can see the cluster IP, which Kubernetes will use to load balance the requests to that IP address between the different workload containers. Okay? And also, if we do microcades kubectl-n OSM to specify the namespace, and then get the pods, we can see that for every application there is an operator pod, right? Which totally makes sense because when we were explaining the Kubernetes charms and so on, we could see the operator, right, that was in a separate container, which in this case it is the NVI gates operator, and then we can see the workload container, which is the NVI gates-o. Okay, so that's a good thing to be aware of, and also to understand all the concepts in a real situation, right? So I don't know if anyone has any questions regarding this. If you do, please feel free to ask. Okay. Is there any question in the chat? Okay. So now we will go back to the presentation, and we will now show off how can we operate with our workloads. In the first part of our session, we were mentioning the life cycle, configuration, operation, and integration. So we are going to show an example of each one of those operations that we can make in our workloads. Okay, I can see that many of you have already done successfully the initial setup. So congrats, it's a very good job from your side. And now we will start with the life cycle scaling. For instance, for example, one application that is the NVI. Okay, so basically, so I
think point out the scale one, right? Where's your
NVI? NVI here.
Right, you've got a single unit there of your NVI application, right? And you want to scale that out to have 3. Yeah.
So now I'm going to do Juju, scale application, NVI, and then the number of units. Okay, if you don't know which parameters you need to pass to each one of the functions, you can do Juju scale application. That does help, and it will just show you a clear message of how to use the command. Okay, so I'm going to move forward and do Juju scale application NVI gates 3.
Or watch the Okay, all right.
And now we can see that there are 2 more units that are being installed, right, or deployed. Okay, so these units, you see,
you see the triggering of events in related applications, right? We changed NBI Kates, right? We changed the northbound interface of OSM, scaled it out, but that requires those other applications to be aware that there has been a change in something that they are integrated with. And so that's why you see the scattering of events through the system. And the charms for each of those other applications are receiving an event and dealing with that event. So you saw them switch into maintenance mode as they were making changes effectively to accommodate that. You see that in Kates?
Yeah, of course. Okay, so here we can see that there are now 3 pods of NBI, and still we have one operator, which is the pod that operates the 3 workloads. Okay.
Somebody earlier asked a question about scaling decisions and auto-scaling. This is a place where, in fact, the scaling decision might come from the bottom or it might come from above. So we just manually scaled, right? We were pretending to be OSM. OSM's taken a policy decision to scale that function to 3 units. So OSM can go and ask the VCA to do that, right? We did that manually as a human operator directly to the VCA. But OSM would normally take that through its rules and it would tell the VCA. In the case of Kubernetes, or in the case of a cloud with auto-scaling, that scaling decision might have come from the bottom. So actually, Kubernetes might sometimes say, for reasons that you don't need to understand, I've decided to make another NBI case. So in that case, Juju can learn about the scaling, and it will then essentially propagate the events to enable the other applications related to that to be aware of that scaling event.
Yeah, exactly. And just to mention, if you were watching the events that were happening, we could see events in Kafka, in Mongo, and in Prometheus that are the 3 charms that requires NBI. So NBI requires those charms, right? And then we saw an action in the UI, or an event in the UI, because the UI actually needs the NBI to make the requests and make the calls. And so we could basically saw only the events in the charms that are involved with the NBI. And it's a very useful, I'm going to show you a very useful slide that Dimitri showed before, which is this one. Okay, so in this case, this workload in the middle is the NBI. Okay, let me make it bigger. Okay, so this workload in the middle is the NBI. And the workloads that are attached to the NBI are the MongoDB, Kafka, Prometheus, and the UI. So we were only seeing events on those workloads, and the rest of the workloads, for instance, the arrow that has no relation with the NBI, couldn't see what was happening. It's so in this this make it very easy to model very well the application, so that components that don't have nothing to do with another components don't interfere one with another. So it make everything very simple, and each charm can be focused only in the things that matters.
I think we have to be careful when we say everything very simple. This is a distributed system. And everybody knows distributed systems are complex. But the point here is to make it possible to write an operator that only needs to deal with the things that it really needs to deal with, right? I think there's a second important consequence, which is reuse, right? This operator for this workload can be reused in many different topologies where there are other things that are outside of its event horizon. So for example, my Prometheus charm can be used with OSM, but it can be used with lots of different other charms, and it only ever knows about the charms that are directly connected to it. And so it can't know about things further away in the graph. That means that the developer of the Prometheus charm can't accidentally hard code things into their charm, which happen to be true when they're running it, but wouldn't be true for anybody else. So it's a very subtle way that charms help you write better reusable operators, because they very carefully shape what you can see to ensure that you can't accidentally hard code things that wouldn't work in some other environment.
Okay, so let's go back to our deployment, and I'm going to see if everyone has successfully if everyone has successfully done the life cycle operation or the scale out. Okay, yes, please update the spreadsheet so that we can have an idea of how many people have successfully deployed. Okay, yeah. Perfect, perfect. How is the experience so far? Are you, anyone can talk if you want. If you have any feedback or something, just tell us, because we are very, very interested in your opinion. Okay, so many of you have completed the life cycle. I can see that, well, everyone has completed that part. So now I'm going to move forward to the next step. The next step is to configure one application, and the configuration that we are going to do is changing the NVI image. Okay, so well, I know the command, so I'm not going to look at the slides. Okay, so if we do config NVI gates, we can see all the configurations that NVI has available. Okay, and one of those is the image. It's pulling from the upstream images with the tag 7. Okay, open source MANO /NVI 2.7. Okay, so basically what we need to do is, for those changes to be applied, is to execute config NVI gates, then the name of the configuration, and after that the value that we want for that option. Okay, in this case we will just use open source MANO /NVI. Okay, so now the config change has been done, and then now we can see that there are 3 units here, right? NVI, the first unit, the second, and the third. And if we see this, we can see that one of those is being terminated. And that's because we have changed the image that we were using. So Kubernetes will do a rollback of those units. It will start by killing one of those, then creating the other one, and when it's in a ready state, then it will continue with the rollback. So this is a very good thing, because imagine that we are in production, we have 3 MVIs, and we want to do a patch of one image because we found a bug, and we patch it. We make the next Docker image or with the fix, and we are doing a rollback and updating the image. So imagine that we made an error or we made a mistake, and we introduced one bug there, and the MVI is not even started. Okay, let's imagine and put us in that position. Then the first unit that is being updated will fail, and it won't continue with the rollback, right? So we will still have the other 2 units available and ready. That's a very, very good thing of Kubernetes. And okay, as you can see here, all the, well, we have already 2 units updated, okay, with the new units. And now it's going with the third one. And we can also check this in the kubectl with the kubectl command. Okay. Okay, yeah, I was too slow, and those are already deployed. But we can see the age, that the age is of about seconds. So those pods are new, and they are using the new image. We could also do something like describe pods and the name of the pod. And there we can see the whole spec and everything with all of the configs and so on. And there we can basically see the images, the image that has been changed. Okay. Okay, so how many of you have finished this step? Okay.
So let's wait for the answers a little bit.
Yeah, I see that many of you are writing now that it's everything okay. So we are very happy to see that. Any questions so far? There's one thing that we can see here, and is the leader election concept that we were mentioning before. If you see, all the components, all the units have an asterisk here near the unit name. Okay, so all of them have them instead, except from 2 of the MVI units. So this one that has it is the MVI leader. Okay, so it's good to understand this concept, and well, yeah, basically that. Okay, so now we will move forward with the next operation. For example, in our case, the MongoDB has an action that is backup. So we could basically run that action on one specific unit. Okay, let me copy paste. Okay, so I just ran the action MongoDB in the MongoDB case/o unit. The action name is backup, and we can see the status of it with the UU show action status and the ID of the actions. Okay, if you see here, the status is completed, so it's it has already been executed and everything. And if we do UU show action output 1, okay, then we can see here that it was dumping some OSM users document and so on, and we could basically copy the backup from the pod, because the action is executed in the workload pod. Okay, so if you can update the spreadsheet so that we can see how all of you are progressing, it could be, it's going to be, okay. Then even see the chat. You're still running, okay. So I'm going to see the spreadsheet. Okay, I see that many of you have already almost finished everything, so it's very nice to see. Okay, yeah. Okay. Okay, that's very good. Congrats on your side. You're doing a very good job. Okay, so let's continue. And now we will add, or we will do the integration, an integration operation, which basically will consist on deploying one charm, one new charm that is Keystone, and we will relate it to several components, which are NVI and the MySQL database. Okay. So basically, we're going to deploy those. And we can see how the Keystone is being deployed and how all the related charms are, you see, the MVI and also the MariaDB is an executing state. So those are triggering actions in the dependent charms. So it's very similar as a very similar behavior as we saw before when we updated the NVI scaling it, that the related components, the related charms, could see some things changing, right? Okay, so please update the spreadsheet when you are finished with that. Okay, yeah, I see that now you are writing okay in the spreadsheet. So just some of you haven't updated it yet, but okay, it's just I think a matter of time. Okay, so we have finished the hands-on. We have shown the lifecycle, integration, configuration, operations with Kubernetes workloads. And we have basically finished this part, but now we will walk through a charm so that we can see how it looks like in code, okay, a real Kubernetes charm. And so you can have some exact examples of it. And okay, so my colleagues will paste the links for the charms. And well, we basically chose two of those charms that are Zookeeper and Kafka. And I will walk through all the files that are in there so that everything is understood by all of you, okay? And well, we will start with the Zookeeper one. So this is the repo, okay? We have several files here, and okay, I'm going to make it bigger. Okay, let's start with the metadata. Okay, the metadata is basically one YAML file in which we specify the name of the term, the summary, like a description, and we specify that the series is Kubernetes. We can also specify the minimum UU version that that term requires. Also, we can provide the storage specification so that UU tells Kubernetes to provide a volume or persistent volume claim for that pod, so that it can that volume can persist even if the pod is killed. So even if the unit dies, then it will come up again, and the storage will be still there. Okay. Then here we specify the relation that this term, in the case of zookeeper, provides. Okay. So the zookeeper provides the zookeeper relation, and then the Kafka, for those that are not aware of this, but then the Kafka will require the zookeeper. So the Kafka will be waiting for zookeeper because it needs zookeeper. Okay, I don't know if that makes sense, but for you guys, or if you don't understand, please speak, and I'll try to answer the questions. Okay, so and also we can specify the deployment type. In Kubernetes are mainly two types of deployments, which are stateful sets and stateless applications. So the stateful sets usually have a dash number at the end of the pod, okay, and they maintain the same names, okay, and the deployments that are stateless have usually a random name. So, for instance, if I do microcase kubectl -get I can see that the UI is a stateful, or it's a stateless, sorry, but the Kafka is stateful. Okay. Okay. So, and we also can specify the service type, let's say. If we specify here cluster, then, which basically is what usually it's
sorry, how did you see that it was stateful and stateless?
Sorry, I didn't understood that.
How did you, when you do like the get bots, you tell that you know Kafka is stateful and the other was stateless, but I didn't get how do you, could you please just repeat the last command again?
Show the metadata.
Oh, okay, I will show the meta. Okay, here, this part.
Yeah, that's the type is stateful, but you show it within the command line.
Oh, okay, right? Okay, so, for example, I will get both Kafka case, I think like this, okay. Okay, yeah, this one is, wait a sec. Just for you to put it more clear, okay. 1 sec. Okay, so yeah, this has a -o, okay, and this has random stuff, okay. This is stateless, and this is stateful.
Okay, I see. Perfect.
Okay, that's feel free to ask any questions, because I think many of you could have the similar questions, and if you ask them, everyone can learn more. So thank you very much for that. Also, if we do UU status, we can see here that are IPs in the application level. Those are cluster IPs. So here in the deployment, the service type, it says cluster. This means that the Kubernetes will assign a service, a cluster IP service to that specific application or chart, okay? If there are other services like load balancer, so in this case, we haven't configured our Kubernetes with any load balancer, right? But if we had, we could put here load balancer service, and then instead of Kubernetes assign a cluster IP, which is only accessible by the bots in the Kubernetes cluster, it will be assigned a load balancer IP, so an IP provided by the load balancer, so that IP it's accessible from the outside. Because the Kubernetes, when you configure a service with a load balancer, it usually uses the load balancer from the underlying cloud. So imagine that you have OpenStack deployed and you deploy Kubernetes on top of that. So that Kubernetes will use, for example, the Octavia load balancer service from the OpenStack to provide load balancer, to provide IPs provided by the load balancer. Okay. In case of in our case, we could enable the MetaLLB plugin or add-on to MicroK8s, configure one range of IPs, right? And then Kubernetes will assign load IPs from those from that range of IPs configured in the MetaLLB, right, to the charms or to the applications that have the load balancer service type. Okay, so I don't know if this is too much information for you. I know many of you could have a background of Kubernetes. Some one of you maybe you don't have that background. But anyway, if you have any sorry, if you have any doubts or anything, please feel free to ask me whatever you want through Slack. So I can answer, and we can also have meetings in Hangouts to answer any questions that you have in regarding this topic, and I'll be very glad to help you all on updating your on Kubernetes knowledge or whatever I can do. Okay. Okay, let's continue. Okay, so we're just seeing this metadata, which is pretty simple, pretty straightforward, and so on. Okay, so now let's go to the config. In the config, we see here the image we are using, that by default is this one. Okay, the client port, server port, leader election port, and number of units. Okay. These things, this leader election has nothing to do with the leader of the unit done by Juju and so on. It's a zookeeper specific thing, so that you don't get confused, right? Okay, so we have these options here, and we can go. Okay, let's go to hooks. Hooks. I think Dimitri explained that before, that this is a symlink to the actual file in which the charm code is placed. Okay. So if we can see the code, let me zoom out. Okay, because this is very interesting. If you see you cannot see anything, okay? But just for you to be calm, in more or less 100 lines of code, we have here the all the logic we have to build our operator. So this is the operator code, and this makes possible for you to deploy the Kubernetes. Sorry, I'm mixing words. To deploy the Zookeeper charm. Okay. And also we will see later the Kafka charm, and you will be amazed of how similar are those two charms. And once you have written one case charm, you can write all the case charm you want. Because if you understand one, then the rest of them are basically the same logic, because the actual workload, the actual intelligence of it is in the Docker image. So that it's really, really simple to write Kubernetes charms. Okay? So now that we've seen the code in a high level view, let's deep into it, and I'll try to make it as understandable as I can. And if you have any questions, please also feel free to ask. Okay. Okay. So here we have several imports. Okay. And we define here the Zookeeper charm, which inherits or extends from the charm base object or class that it's defined in this place. Okay. So here we in this line we specify the state. Okay, the state object, which instantiates an object from the stored state class, so that we can basically set their key value data and access it from different events. So imagine that the install event is triggered. We can set one value there. And then in the config changed event, we could check what was the key that was assigned in other events.
I don't see a screen.
Yeah, of course. Yeah, okay. Okay, so let's continue. So here in the init method, we basically initiate our, well, it's basically the constructor for this Zookeeper. Okay, so it calls the charm-based constructor. And then here we save, or we store one key that is started to false. Okay, so we just do self, that is the charm, dot state, which is the object of the stored state. Okay, then set default is started equal false. Okay, I think that's clear. Okay, well, this object is or this variable is there. We may know what's that for later on. So then here we can we check if it hasn't started, then we put this to started because it's running through the to the constructor itself. Okay, and here we basically specify the events we want to observe. Okay, so basically what we do here is self.on.onChanged self, which basically will trigger this function, the onConfig changed. Okay? Same for start, same for upgrade. Okay, so if we go on and jump to the onConfig change, well, no, sorry for that. The first event, the important one now is the onStart, because this is the first event that is called. The onStart event will be called when the charm is firstly deployed. So we do unit equals self model unit. Okay, I think there's a slide that can help you seeing this, which is this model representation. So self, the charm, dot model dot unit. Okay, and we have here the unit of the Zookeeper application. Okay, so we can basically set unit.status equal maintenance status applying pod spec. Okay, so basically we are setting the status of the unit. Then we create the pod spec. Sorry. Okay, so we call the make pod spec function here, which is basically this one. And here we access the config, which is the previous file that I shown, the config.yaml. Okay, we show the store the config in this variable, and then we define the spec. Okay,
or ask you to put it a bit bigger.
Okay, you want it to be bigger. Okay. Okay. So basically, this is the. I think that's much better. So there we specify the spec. Okay. We specify the version of the spec. Okay. My colleagues can send you some links where this spec is specified. So you can see that I haven't just invented all of this, and so that you can have the source of information where all of this data model is specified. Okay, it will take them a couple of minutes to find the links, but it's okay. Okay, so we here specify the containers. The name of the container, well, the containers is an array because we could basically have one pod with multiple containers using multiple images. But in this case, the Zookeeper only has one container. So the name is can be accessible from self, framework, mobile, app name. Okay, the image is one of the configurations. So we are basically doing self, framework, model, config, and then accessing the key image. Okay. And we are setting the ports in which that Zookeeper is listening. Okay. Then we add inside the Kubernetes key some attributes or some components that are specific for Kubernetes. So just to give you a background of some things that you can do with Kubernetes. It's for those that are used to using the Docker Swarm and the health checks and so on. This is more or less similar. Okay, so the readiness proof is basically an action that let's say that Kubernetes does to make sure that all the pods are ready. Okay, so here we specify the TCP socket and we specify the port, client port that we specified in the config. Okay, so this means that Kubernetes will, let's say, ping this port of the pod. Okay, and if suddenly it stops, then Juju will know that and will show a message in the Juju status of waiting because Kubernetes has detected that the pod is not ready. Okay, and here we can specify the initial delay seconds. So once it's deployed, it will wait 10 seconds. Okay, timeout seconds. So what was this? Well, I cannot remember.
If it's not responding after 5 seconds, it gives you a timeout error.
Okay, yeah, that was it. Sorry for that. So the timeout seconds are basically if Kubernetes is trying to ping and the response is more than 5 seconds, it understands that it's not ready. Okay, and failure threshold is if 6 times the pod is not ready, then it will understand that the pod is not ready, basically. Okay, and then we have the liveness proof. This is very similar, but it's not the same. So we have to be careful here. The liveness proof basically tells Kubernetes that the pod is not alive, and if it doesn't pass this proof, Kubernetes will automatically destroy the pod and redeploy it again. Okay? So, well, those are Kubernetes specific things that it's good to know. If I repeat, if some of you don't have enough experience with Kubernetes, you can ping me on Slack, and we can have conversations or Hangouts meetings, so I can explain you all of this in more detailed way to a specific workloads that you want to deploy or develop or whatever. So I'm very glad to help you and walk through this process. And the last thing is the command. So I think this is fairly similar as the command that is specified in the Docker file. Okay, so basically what we do here is we start the zookeeper with the number of units that we set in the config and so on. Okay, and a couple of more data. Well, this is specific for this unit. Okay. Well, let's move on. And the on config. Well, let's go back here. Okay, here we have the self framework. The observe on config changed. So in this function, basically what we do is we the trunk will trigger this event, okay, when some configuration has changed. If the configuration has changed, then it will make the new spec, okay? With the new configuration, let's say we have updated the number of units, so the port or whatever, okay? So we will build the new spec, and we will apply that new spec to the, we will basically apply the new spec. Okay, I forgot to tell that here. Okay, let's. I'm going through that later. Okay. Well, basically, in the on start function, we created the pod spec. Okay, applied it, and it was in this state. The workload will be deployed on Kubernetes. Okay. And we also take care of some things for the Kubernetes, for the zookeeper interface. So we get the host with the application name, we get the config object, and with the zookeeper relation, self model get relation zookeeper, we take the application data, okay, the relation data here for that application. And then we set the application data. In the application data, we set the host, the port, and the REST port, which are basically the same. And then we emit the event saying that the zookeeper is available, okay? So that later on, when someone joins, it can see that the zookeeper is already available and it has already data on that relation data. Okay. Okay. So in the config change, coming back to the config change, we should apply the new spec with the new configuration, and the Juju controller, or sorry, the operator.
Okay.
Yeah. What?
Can you continue your 6 months? Built to the second.
Okay, I think someone is speaking. If you have a question, feel free to ask, but if not, please get muted. Okay. Yeah, as I was saying, the config change will trigger, when we have an spec, okay, here, yeah, that we have, if self-state spec is not equal to the to the new spec that we are building here, okay, we have to apply the new spec. Okay, let's go to the apply spec, because I think I haven't showed that yet. Okay, so in the apply spec, we first check that the unit is the leader, because only the leader can configure the pod spec. And if it is, then self-framework model pod set spec to save the basically the spec into the stored state, so that later on we can check here, for instance, if the spec has changed or not, looking at the previous saved spec. Okay, I think it's I think those are new concepts from for all of you, but I think it's a very clear and clean and also explicit way to develop and to show all the different events that the charm can trigger, and so you can basically see very well how where is the code of each event is where is it coded actually. Okay, so we have the config change here, we have the on start here, and then we have the upgrade charm, which is the last event that I was going to explain, which is basically very simple. It just do an upgrade charm and calls the on start event, because if the charm gets upgraded, then we basically want to execute all of this again. Create a new pod spec and so on, and then apply the changes and so on. Okay. So basically, this is it. And let's go back to, let's go to the other charm, that is Kafka. Okay. So here in Kafka, now you will notice that we are going to go much faster, because this charm is basically, it has basically the same structure. It will only change a couple of details that are for the relation and for the pod spec, because obviously the pod spec for the Kafka and for the for the zookeeper are different. Okay, but you will see this a lot of more familiar than before. Okay, so we are again seeing the metadata.yaml. Here we see the name. In this case, is Kafka Gates. the summary, description, service Kubernetes, the mean UU version. Okay, it's everything is the same. The storage, in this case, the storage is in another location because the Kafka data is stored in that specific file system location in the workload containers. Okay, so but basically it's very, very similar. You only have to know how your workload works, okay, and then decide if the workload needs an storage or not, and if it needs an storage, then know where should it be mounted inside the workload pod. Okay, let's continue. Then here we specify the requires interface. So the interfaces that the charm requires. In this case, Zookeeper. Okay, and the Zookeeper interface, the name of the interface is Zookeeper. And the same as before, the deployment type is stateful in this case, and the service type is cluster. So it will be assigned a cluster IP to that workload. Okay. Then go back to the Kafka, and here we can see the config. Okay, so in the config we have in this case three main options that are the image, the port, and the hostname. Okay, we could add more. Okay, we make these terms very, very simple, very clean, so you can all understand them very well. Okay, and well, basically I don't have anything more to explain in this file because I think it's very straightforward. But if you have any questions, please stop me whenever you want. Okay, so yeah, we have those files. Then, well, the hooks that are pointing to the other to the source chunks.py. Okay, we have here the interface and so on. Okay, so let's go to the churn.py. Okay. So here, well, I'm going to zoom out a bit. So here we can see that the code is fairly similar. Well, a couple of more lines, but we will see what's different. But almost everything is exactly the same as before. So it's you will feel more comfortable this time when looking at the code. And I just want to point out that in Kubernetes, when you have the workload, the important and most difficult thing is to operate the workload. Everyone can deploy workloads. With Helm, you can deploy workloads, but the real thing is that the real important thing is that you need an operator that can operate the workload. Okay, so I just want to point out that this code that you are seeing here is basically an operator. Okay, so it's very, very important. And later on, we'll see some examples for proxy and native charms, and you'll see that it looks very, very similar. Obviously, they won't have the spec, the pod spec, because the machines don't need the pod spec. That's only a Kubernetes thing. So a couple of things might change, but with the same framework, with the same technology, you can operate both machines and Kubernetes workloads. That's a very, very good point, so that when you hear the operator word, you can immediately associate that concept with the chart. Okay. And okay, perfect. So let's continue. Here we have, sorry. we have some imports, same as before. Then we import the zookeeper interface, obviously, because this is needed in the Kafka charm. We also have the state, same as before. I'm going to explain it again. So this is very, very clear, I believe. Then we have the constructor. Okay, same as before. We are setting the is started equal false in the state. Then we are initiating the self zookeeper object with the zookeeper client, that is basically the relation object. Okay, and here we we are, well, same as before. We are setting the is started value to true and so on. Okay, and then here we observe the same events as before. Okay, everything it's exactly the same, but we also will observe if zookeeper is available. Okay, this is very, very important. So when the self zookeeper, which is the relation object that we have here, on zookeeper available event that was emitted, let me go back very quickly so that you can remember. Okay, so here at I'm going now to the zookeeper code. Okay, so here we were doing self on zookeeper available emit. So we were emitting that event. Okay, so that now the Kafka can trigger itself, okay, when the zookeeper event, when the zookeeper available event is triggered. So when that happens, it will call a on config change that will basically reload the pod spec and everything so that it has the data from the zookeeper relation. And now we'll see clearly that in the code. Okay, so let's start with the self on start event. So when the self on start event is triggered, it's triggered, then self will handle. Self is discharge. So let's go to the definition of the on start function, which should be here. Okay, on start. So when that event is triggered, that is triggered when the pod is firstly deployed, then it will basically do exactly the same as in the zookeeper charm. It's exactly the same. It will get the unit from self model unit. It will it will set the unit status to maintenance, and it will show this message, applying pod spec. It will get the pod spec from the make pod spec function, and then it will apply the spec. Okay, let's go first to the make pod spec function. Okay, so in the, just 1 second. Okay, so the make pod spec function. Here we get the config from the self framework model config object. And then we'll set the spec dictionary with all the, well, same as before in zookeeper, with all the data for this pod spec. So, same as before, in the containers key, we put the array of the different containers that the Kafka service or the Kafka application will have. In this case, it will only have one container. Just to remember, for those that maybe don't listen in the first part, if you miss that part, then each pod can have multiple containers. It will depend, obviously, in the workload that you are deploying. Okay, and so in this case, the container that we are deploying, we are specifying the name here in this name key, and we are getting that name from the self framework model app name. Okay. Then the image, we are getting it from the config that I showed before. So same as in Zookeeper, config, and then we access the image key, the image option. Then we specify the ports that are exposed so that Kubernetes knows which ports will expose for that specific container. This is very important because it's mainly a security matter. Kubernetes will only expose those ports that are specifically specified in the pod spec. Okay. In the previous example, the Zookeeper had 3 ports, one for literal election, another one for server, and another one from client, if I recall correctly. In this case, the Kafka only has one port, which is specified also in the config. Then we can specify here some configuration for the Kafka container, from the Kafka workload. These are the environment variables that will be injected to the workload pod. Those are specific Kafka keys that I will, I can explain, but are not the important thing here. If you understand Kafka, then you will recognize those. You may recognize those values, but again, this depends on the workload that we deploy. If you go to Docker Hub and to MySQL container, you will see there a different set of environment variables that the Docker image supports. So those variables are the ones that you may want to include in this config dictionary. Then, same as before, we have the Kubernetes key, in which we specified specific Kubernetes things, like readiness proof and liveness proof. In the readiness proof, we are checking the TCP socket so that the port is open. Okay, so if suddenly the application is not running, or it has been it's down or something, this Kubernetes will know because it's continuously pinging or checking if that port is available, and if it's not, then it will show a message that the readiness proof has failed. Okay, so the container has that the container is not ready. Okay, just I want to show one thing in microcades so that this concept gets really understood. So here, if we do kubectl get pods, we see a column that is ready, and there we can see that if it says 1/1 is that one container from all the containers that are deployed, which is one, are ready in a ready state. In the case of LCM that we haven't configured correctly, it says 0 of 1. So none of the containers deployed are ready. Okay, let's continue, and please, if you have any questions, please ask them. Then the liveness proof shows, I made a different, a slightly different thing here, that basically instead of checking the TCP socket, one specific port there, what I'm doing is I'm executing one command. So that command it's executed correctly, then it will be a success. If it fails, then it it will show that that's not alive. This is a very, very specific thing, a very specific command that basically checks something Kafka. Honestly, I don't remember exactly what this does, but it doesn't matter. The thing is, the important thing is the concept. Okay, let me drink some water. Okay, so and then the command, it's exactly the same as before. We specify here the command that we want to execute. In this case, we execute the some script that is inside the Kafka, inside the Kafka container. This is a very specific thing for the Kafka workload. Okay. Just one sec. Sorry for that interruption. I was checking something with my colleague. Okay, so let's continue. Where were we? Well, basically we were explaining the onStart event, okay? And we were in the make pod spec. Now we get the spec here and we apply it. Let's go up here and basically same code as before. Nothing has changed. So it's very, very clear that almost every operator handles or behaves in the very similar way. So the code can be, the skeleton of the code is common to all the operators. Okay, let's go to the config change event. So the case of the config, then we can do or we do zookeeper self zookeeper that basically will get a list of or an object of the zookeeper relation data. Okay, and this zookeeper has all the relation data that we set before. Let me open another tab. Okay. Okay, here we were setting the zookeeper data host to the host and to the zookeeper data port to the client port, so that the Kafka can now compose the zookeeper URI with the host, okay, and the port from that relation data. Okay, so here you are seeing in a very clean way how the zookeeper has set application data or relation data, and then the Kafka, that means zookeeper, is getting that relation data. Okay. So again, if the zookeeper is available, okay, it will continue. If not, it will throw an exception that is a zookeeper error, and we will set the status of that unit to that error status, and we will return, and then it will be execute this later in another time. We could also replace this return or add into this the event.defer, which basically will defer this event, and it will be triggered later on. Okay, let's continue. So we get the config again. we set the config zookeeper URI to this, and we will get the new spec with the make pod spec. I'm not explaining this again. Well, I can show it, of course. But it's basically the same thing. Well, the important thing here that I didn't explain before is here. So we specify the zookeeper URI with the config zookeeper URI that we are setting here. Okay? I think it's very understandable, but again, maybe for me it's, well, I have worked with this for a long time, and maybe for me it's easier, obviously, but I have to say that the learning curve is very, well, it may scare you at first sight, but as you can see, the concepts and the things are very clear. So it's a very, very clean way to develop an operator chart, okay, for Kubernetes. Okay, so basically here the code is basically the same. Okay, I'm being told that I have only 5 minutes left, so I'm going to be faster. Okay, so this is the upgrade charm that is basically the same as before. Okay, so what I'm going to show you now is the last slides. Okay, these last slides. Okay, so we did the walkthrough through some charts. So now I have put the three scenarios of three different of three different charms that you may want to deploy. Let's say you want to deploy a cage charm through OSM. Then you will go to the VNFD, and you will have to add this code, this YAML, into the VNFD package. Okay, specifying the Juju bundle of the a Kubernetes bundle. Okay. Also, I have put here a base code so that any of you can start writing your own charm in a couple of minutes, let's say. And only for your information, I did the Zookeeper and the Kafka charms in more or less 1 hour. Obviously, I have some experience and so on. It may take a bit more from your side the first time, but you will see that this skeleton that we have put here, it's exactly, it's very, very, very similar. Okay, so this is the metadata. Okay, this is the config. Okay, which basically has one image. You could add more things there. And then the source, it's exactly the same. You will see that it's almost the same. Here, we observe the events, okay? Then here we do the apply spec. Here we make the pod spec. It's basically the same as before. We do the config change, and I haven't even touched these functions of, or almost touched these functions of config change, start and upgrade charm, because those are basically the same in all the containers or in all the charms that you want to deploy. So just I've said that is important. And also, you have a different, you can do a different approach. And if you want to do a proxy charm, in which you will, as remembering the thing that we were talking before, the proxy charm resides or lives in a different place from the workload. This workload, in this case, is a machine, not the Kubernetes workload. Okay, this is how the VNFD will look like. We specify here the VNF configuration, the Juju charm that we want to deploy, the initial config primitive, that is basically the actions, okay, and the config primitives. And later on, sorry, I was too fast. Okay, yeah. So basically, this is the VNF descriptor, okay. And I see I put here the code for the skeleton of every proxy chart, okay. And same thing for the native chart. Okay, the VNFD descriptor is slightly different because, as we said before, the charm and the workload, in the case of the native charm, are in the same unit, are in the same place. So the charm must be a BDU, must be specified inside the BDU configuration. Okay, and we say here Juju, specify the charm and the name of the charm, and then we say proxy to false. So we are explicitly saying that this charm is not a proxy charm, so it's not deployed in the VCA, it's deployed inside the machine. Okay. I'm running out of time, but I think I've covered almost everything that I want. Here I put the skeleton, the base of code for the native charm. You can walk through it. It's very, very similar as in the Gates charm. We obviously recommend to use Gates charms. You can use whatever you want in the because it will depend the charm that you use in the scenario or in the workload you're working with. Okay, we all know that everything. Well, now Gates is getting more famous and it's the new thing, and it's faster and so on. As you seen before with, as you have seen before with the workloads, it were deployed really, really fast and. Well, and you know, but it will also depend of the scenario. We can help you with any questions that we have. We are finishing now the session, running out of time. We will have now the lunch break. But just as a summary, I would like to say something that I said before, but is that when we were talking about Kubernetes workloads, we were mentioning that the workloads need to be operated by an operator. So all the code that you have seen during this presentation, all the charms code, that is an operator. So in this session, you have basically learned how to write an operator charm. Okay, that technology, those mechanisms are useful for both deploying operators in a Kubernetes scenario, in a Kubernetes world, and we also use the same structure, the same framework, the same technology to do an operator for machines, for VMs and so on. So it's important that you relate those concepts between the operator and the charms that are basically the same. So I will put my email in the chat, okay? So that all of you can, well, my colleague can put it for you. I recommend you all to copy that email, so you can find me in Slack. You can also write to the OSM Tech mailing list. You can write me personally in a personal email if you are not familiar with Slack or whatever. But you can write me, ask me questions, tell me about the workloads that you want to deploy. Me and my team can help you to get started very fast in writing operator charms, and yeah, we will be glad to answer all of your questions, and we are open for anything that you want.
So after lunch, we're going to get hands-on. So keep your VMs fired up. You may want to download your favorite code editor so that you can actually hack on charms. And we will do some quick iteration on some charms, and then perhaps step back and go and look at the VNFD again. So now you understand the underlying operations code. We'll come back up and show you how you expose that operations code through the GUI in OSM as a series of operations primitives. So keep the VM running. If you have a favorite text editor, etc., then go and get those. Otherwise, have a good lunch, and we will see you in an hour and a half.
2:30 local time.
2:30 Central European time. All good? All right. Thank you very much.